Before we jump in, a couple of announcements. One, we have our field trip permission slips over there on the black table, so if you wanted to go, please pick one up. I was hoping for the school cash to be online as well today, but our bookkeeper isn't here today, so hopefully tomorrow, but I will let you know en route as soon as that happens. Remember, you must have had a C or better in the first 9 weeks in order to go, although progress reports are just around the corner. In fact, our grades are due on Thursday. So if you didn't get the grades for the first 9 weeks and you are able to have a C or better in the second 9-week progress report, I'll let you guys go too. But of course, the people who are at first get first dibs. So I will let you know as soon as I can with the post on rooms. So make sure that we're checking rooms every day so that you guys can be first to pay for the field trip. Cool. Also, I posted the information stuff about our egg drop project in rooms as well. So we have about a month before that is due, right before Christmas break.
Yeah.
Smashing good time.
I haven't even started.
Yes, yes. All right. Did I talk about centrifugal force or centrifugal force last class? All right, cool, good. Because I had forgotten to do it during my 1A. I hit it on my 2A, but then I forgot about you guys. I forgot if I had done it with you guys or not. So.
No.
All right, so today we're talking about advanced circular motion problems. So we talked some last class about identifying what serves the role as the centrifugal force, and so now we're actually going to work out some problems. If you look on the videos, go to the last week's reading or watch. Again, I'm posting things to watch now, so you've got more options in terms of how to get your information. You can either read or watch, but reading will definitely give you more. Watching is less, but there are obvious advantages to watching. It takes a lot less. But yeah, so based on how well you, or not how well, but based on your learning style, you can watch or read or both if you want to do that. And then you'll be good to go. Okay, so here we go. So let's talk about, so first we'll talk about cars on circular tracks, and then we will end up with roller coasters, which will tie in greatly to our field trip that we're taking here in just a couple of months. Yes, super fun. All right, so let's take a look at our first one. So we have a car on a flat track. So imagine a track on the ground. It is completely flat. There's no banking here. So the car is going to be going around in a circle kind of like this, where this will be the center of the circle. The car is on the track, and we are looking at it from the back as it goes away from us and around the circle like that. We're going to assume that it's at a constant speed. Okay, so I want to find out what is an expression for the speed of the car as it relates to things like, I don't know, maybe like the radius of the track. We're going to assume that it's going to the center of the car, although technically we're always going to treat our car and our objects with as point-like, as in they don't take up space, so the R is going to be constant. Of course, we'll have our mass and the coefficient of friction, U. Good? That's ready? Yeah. Excellent. Right. Okay. So we got the mass of the car M, and we've got our coefficient of friction mu. Let's take a look at our forces. We're going to approach the man, I've been doing this all day. I'm tired. We're going to approach all of these problems the same exact way. First, we're going to draw a picture. Second, we're going to draw our FBD. So let's do that. FBD, we're talking about our forces, and of course, we've got our force of gravity, and the normal force pointing straight up because the normal force points perpendicularly away from the surface. So there we go. And then, well, but remember the centripetal force always points towards the
Center.
center. Yeah, so the center in this case is going to be pointing to the left. So what serves the role as centripetal force here?
Friction.
Friction, yeah.
I'm on a roll.
So it's not the force of gravity, and it's not the normal force. It has to be the force of friction. We talked about that last class, how it's actually static friction and not dynamic, because it's not moving radially either towards or away from the center of the path. All right, good. So I have identified what force serves the role as centripetal force. So then I get to set them equal to each other. So we have our centripetal force is really equal to our force of friction. So now we're going to break it down with their respective equations. We are going to take the typical mass times the centripetal acceleration, where the basic form is going to be the v squared over r. So that's going to be m times v squared over r. That's going to be our centripetal force side. And then our friction, of course, we learned about that before. That's going to be the mu times the normal force. Now, whenever we have like FRQs that talk about deriving an expression, and they give you certain terms to use, like we can only have r and mu and m in the equation. Those are the only acceptable things that are allowed, along with constants. So as I'm solving for v here, okay, so the m is allowed, the r is allowed, the mu is allowed, but the fn is not. So I need to get an expression for fn and substitute in to that big expression so that I can work it all out properly, okay? So I notice that, hey, my fn is my upward force and it's going to be balanced by my fg, right? Yeah, because if it's going in a circular track this direction, it's really not moving with respect to the y-axis. So it's at rest in the y direction, therefore my y direction forces are balanced. So I can say, let me write that over here, so my Fn is actually equal to my Fg. And we all know how to find Fg. Fg equals mg. There we go. So I'm going to substitute mg in for the Fn in this equation, and we'll see what we get. So mv squared, sorry, I'm trying to write quickly, but I get sloppy, so I'll try to slow down just a little bit. So mv squared over r is equal to mu mg, and now let's solve for g. So algebra stuff, notice that the mass will cancel as I divide both sides. Interesting. I wonder what that means. So I'm going to multiply both sides by r, and we get rug. Just kidding. We take a square root, and we get the square root of rug. That's not you, that's mu. What it looks like.
Did he say dad joke?
Yeah, I did.
He is.
You missed it, because you were in the bathroom. Sorry. But I can say it again if you like.
Yes.
How do you hold a bat in a cave? Or what is the best way to hold a bat in a cave? By the hand.
Okay. Right. Y'all
Like a baseball bat?
An actual bat that flies down the cave. Yeah.
By the way, do you know?
I don't get it.
So bats sleep upside down, right? Yeah. Okay. So they have to hang on to something, right? So I know that when I sleep, all of my body is relaxed. So how do bats stay attached to whatever they are while they're sleeping?
You probably have a locking mechanism.
That's a good guess. So it just so happens that they're like when our hands are relaxed, they're open. Bats' claws are actually reversed. They are relaxed in the closed state. So they actually have to exert their muscles to open their claws, because relaxed state is actually in the closed position. That's why they can be relaxed and sleep and still hold on to stuff. Cool stuff.
Okay.
I know more than physics. There you go. All right, so let's take a look at our equation. What does this mean? Okay, so now technically, because this was static friction, and we said that this was equal to mu times Fn, that meant that that was maximum static friction force. Okay, which also means that this is the maximum speed that we can go right before we start sliding off the road. Okay, so this is actually our V maximum. And notice what it depends on. So R is going to be the size of the curve. So if we've got a sharp curve, a small r, then we've got a small Vmax. We can't go as fast as if we were to go like on a large curve. Like going on like I-295 and I-95, the interchanges there, they have really, really wide, long, and really big R curves. And you can go at a decent speed. You may not be able to go full like 65 miles an hour, but maybe 50 miles an hour. They have those yellow signs on there that say the speed, that is the recommended speed because there are curves. However, if you get off of the highway and onto a smaller street, that off-ramp is going to be much tighter curve. That R is much less. And if the R decreases, our Vmax also decreases. You might see like a 25 mile an hour yellow sign on those on and off ramps. Because the tighter the curve is, I can't go as fast. Hello.
My minimum speed.
Thank you. Mackenzie, you get to go home. He died the other day.
What?
Yep.
Who?
The guy
Oh
was
yeah, the You Got Mail guy.
the voice of You Got Mail.
I thought
He,
it was-
he got paid $200 to make 4 different recordings for
You Got Mail.
America Online or AOL. $200.
Oh, 200.
Yeah,
Hey, bro.
That's not that
and
bad.
now he's dead.
I always thought it was a computer that made the noise.
You got mail.
No, it was a
Like,
real life
for
person.
real, He just said, he's dead.
Now, nowadays, we could have a computer actually talk. Well, technically back then, we could have a computer talk to you, but it would not nearly sound as human-like as we do now. Technology has definitely grown leaps and bounds.
You should tell Siri, you'd be surprised. No, you wouldn't. No, it's just how she sounds.
I don't know.
I be like, Siri, bro. Make sure you got all your gadgets out. Let me see that. Oh.
Well, I brought this one out, yes.
What is?
It's well, that is the Death Star.
It's their vineyard.
The Death Star, yes.
You know, I
Which
never-
isn't actually a star.
I never watched I've never. I've only watched.
Well, we might just have to watch it on our way to Busch Gardens.
Oh,
I'm gonna pause.
Get out of here.
Anyway, let's get back to our equation, and here we go. So, now mu also changes it. The lower the mu, the slower I have to go. What could possibly reduce the coefficient of friction on our roads?
Water.
Water. Yeah, like when it rains, right? So when it rains, things are more slippery, right? So the mu is not as big. What's the
Ice.
most dangerous part driving wise in terms of friction when it comes to a rainstorm, Jordan?
Right when it starts.
Why?
Because the oil from the cars and the friction, the oil comes up and it becomes really slippery.
Yes.
Driver's ed.
There we go. Good old driver's ed. Now, why isn't it the first half an hour and not like the last half an hour? Because like you could think that there could be like more rain after it's rained more. Kyler? The water has more time to seep into the concrete. You're kind of on the right track. Right, exactly.
What's the question?
Evaporate.
Why is it the first half an hour that's the most dangerous instead of like when there's more rain on it, like
Because
during the last half an hour?
The water is not like. cold.
ground.
Ash.
Alright, Bradley.
Because like the water spreads the oil out, or just cars going over it will disperse it.
You're definitely on the right track. Okay, so when it first starts to rain, there's oils on the road, and then there's water. And you guys know that oil and water don't mix. And when it first starts raining, it hasn't had enough time to wash away the oil off of the road. So both the oil and the water are there, making even less friction possible. So that's why the first half an hour of a rainstorm, that is the most dangerous in terms of slickness of the roads, because the oils are still there, the oil and the water make it more slippery.
It's also when people panic the most.
Say what?
That's also when people panic the most.
When it first starts raining, or when they lose control?
Both.
Well, yeah. Cut?
That'd be kind of weird if you stayed calm.
Let's get back to our advance.
Yeah, I don't know who now. So technically, if you go to NASCAR, okay, those tires have no tread.
Oh yeah, they're like smooth.
They are smooth, okay, because they're trying to grip the asphalt as much as they can. Okay. In fact, if you ever see at the beginning of a NASCAR race where they're going slow, but they'll kind of go back and forth and kind of weave stuff. So they're actually warming up their tires so that it makes them more sticky, because hot rubber, it gets sticky, and the more sticky the tires are, the better it's going to grip the track, because these cars are going like 200 plus miles per hour. So I don't know. I'm not really a NASCAR fan, but I've definitely seen some of it. And 200, is that appropriate, NASCAR fans?
That's one of those two.
Yeah. Okay. Yeah. So I mean, a lot faster than I like to drive. Believe you me. Anyway, so the moral of our story is, okay, that it is impossible to drive the same speed around a curve wet that we do dry. Because when it's wet, especially when it first starts raining, the oils are still on there, then our mu is greatly decreased, and so our V maximum is greatly decreased as well. You gotta slow your roll, okay? Slow that bad boy down. All right, now, we also have G. Now, typically G doesn't change here on the Earth, but let's just say that we're playing real life Mario Kart and we go to the moon, okay? Where the G is less, and we have racetrack on the moon. Because the G is less, our Vmax around our curves is less as well. We can't take those curves as fast as we can on the moon than we can on the Earth, but if we take our track to Jupiter, where the G is more, we can go faster around those curves. Very interesting. Okay, cool. So that's going to be a car on a flat curve. Let's take that NASCAR example, because is the NASCAR track a flat horizontal track? No. There's a bank to it. Yeah. So let's do that next. Car on a banked curve. I'm going to leave that up so that we can compare. So same deal here. Here's the center of our curve track, and here's our banked curve. Basically, it's like an inclined plane, but we're not going up or down the plane. We're actually traveling this direction again, like we were before, but this time is on a banked curve. There's going to be an angle theta there, of course, the mass of the car, and we are actually ignoring friction in this particular case, so we're going to call it a smooth banked curve. Smooth, no friction. All right, so I've drawn my picture. FBD is next. Here we go. Force of gravity points down, obviously. And where does the normal force point? There you go, up at an angle. Perpendicularly away from the surface here, just like we learned in the inclined plane here. So there's our Fn. But unlike the inclined plane, we are not going to tilt our axes, because remember that our centripetal force has to point towards the center of the circle, so that is in the typical x direction. So we're just going to leave our axes as is. What serves the role as the centripetal force here? Right? Well, that helps.
It's inclined pointing towards.
Does the force of gravity point in the right direction? No, because that points down. That's definitely in the y direction. I need an x direction force. What about the normal force? Since there's only two, it has to be with the normal force. Does that point directly in the left direction? No, but does it partially?
Yes.
It does. I wonder if I were to break up that Fn into its x and y components. Let's see what happens. So if I draw so there's going to be my Fny, and here's my Fnx. Oh, look at that! I found a left pointing force now. Yeah, so in this case, it's not even a whole force, but it is rather a component of a force that serves the role as centripetal force. Fnx, that's the only piece of a force that we have, so that means that my Fnx must serve the role as centripetal force. All right, so I've identified it, I set it equal to each other. Now again, I'm going to solve the equation down so that I get an expression for how fast we can go, okay? So here we go. Now my FC, that's going to be mv squared over r, just like it was over here. My Fnx, I don't know what this equals. Now, I do know that the angle of the banked curve is going to be the same as this bottom angle up in here. I could prove it, but we really don't have a whole lot of time for that, so you're just going to have to trust me. Not like I would lie to you, but, and if you really want to know, maybe we'll have a few more minutes at the end of class, and then I can prove it to you, okay? But the angle is going to be the angle between the Fn and its y component, just like before we broke up the weight vector, and it was the weight and the y component. It's always with the y component. There you go. All right, so my Fnx, well, I still don't know what it is going to be equal to, but now I know that my Fny, what's true about my Fny and my Fg?
Equal.
They're equal. Why?
Because they're Fn.
Because they're on the y-axis.
Because they're on the y-axis. And what's true about my motion in the y direction?
It's constant.
Constantly what?
The
Constantly
same.
0, yeah. Because we are going to assume, because we're maintaining a set r away from the center, that means that it's not going to slide up, it's not going to get higher, and it's not going to slide down, it's not going to get lower. So the y direction motion is technically at rest, which means that I can set those two y forces equal to each other. So let's do that. Fg is equal to Fny, okay? And we know that Fg is equal to mg. So I've got information about my y component, and I need my x component. Technically, I don't need to know what my Fn is. I just need a trig function that contains both opposite and adjacent. Tangent, there you go, there you go. All right, so we got tangent of the angle is equal to opposite over adjacent. Good old SOHCAHTOA helping us out for you. And even if you forget her name, it's always in your data booklets, your equation sheets. All right, so the opposite over adjacent, that's going to be opposite is Fnx divided by my adjacent, Fny. And then we're going to solve for Fnx using this equation here. So we got our, and I'm just going to pull it this way. So Fnx is going to be Fny times the tangent of the angle. And hey, Fny I found was equal to mg. So I'm going to substitute that in. So we get m times g times the tangent of theta. And there we go. So I'm going to plug that right into our master equation right here. So we got our mg tangent theta. Yeah. And now we get to solve for v. Sweet. Algebra magic. Oh, look at that mass. It doesn't, it cancels out again. Now that's interesting. So the mass canceled out over here as well. So it doesn't actually matter if we have just a driver in a car or if my car is full of people, the mass doesn't affect the speed that is required, or the maximum speed that you can go. Interesting. Now, in real life, things do take up space, so we do have things like center of mass. Like the taller the car is, the more likely it is if you take a curve too fast, it might actually roll over. Hopefully not, but that is definitely a possibility in real life, especially if you were to like if you're going 60 miles an hour and you try to swerve to, not hit a deer or something, and as you're swerving, you are initiating a circular path moving. But if you're going too fast to make that circular path go, then your car starts to slide, and based on how intense it is, it might actually rotate. Definitely want to be careful out there, folks, especially if you have a high car. Now, if you notice also, like sports cars are typically low to the ground and wider. So that's going to give them a better chance of not flipping over, so they can take turns faster because they don't have to worry about the center of mass and the flipping over. But big SUVs, especially trucks and stuff, if ever you see a little sign that has a little truck that's like tipping over, because warning, it's a sharp curve. If you take it too fast, you can tip over. That's where it comes from. Okay, let's get back to our problem here. We're going to solve for v, multiply both sides by r, and take a nice square root. So v is equal to the square root of rg times the tangent of the angle. And this is going to be our v maximum, how fast I can go on this banked curve without sliding off. Now, keep in mind this is without friction, so it's just from the fact that it's a banked curve that we keep it going. So again, the wider our curve, the faster we can go. The more g we have, the faster we can go. And the tangent of the angle. What do you think? With a steeper curve, more angle or less angle, can we go faster?
More.
More? Well, let's take a look. Our tangent function, okay? Remember our tangent function from math? Kind of looks like this, where we've got an asymptote at 90 degrees. Yes. So, and technically we don't have to look at the first part, just the first quadrant. So as the angle increases, the tangent of the angle also increases. And at first it's just a little bit, but as you move on, as you get to larger and larger angles, it increases a lot. So the faster you're going, so the larger the angle, the steeper our slope is, the faster we can go, okay? I wonder, how fast would we have to go if it were completely vertical? Like if I wanted to make a circular room and I were to drive my car around on the walls, how fast would I have to go based on this equation? If the angle is 90. Well, what's the tangent at 90? If you plug it into your calculator, what do you get?
2.
Nope.
Or
The maximum number for, well, no, let me not say that. That's wrong. What do you get? Domain error. It means undefined, right? But in pre-calculus, who's in pre-calc? There you go. So at the end of this year, you will talk about limits. Oh, you've already talked about limits. Oh, very. I'm sorry, what?
That's like the first unit, yeah. Like limit notation and then.
Really? Okay, cool. So what's the limit of this function as we approach 90 degrees? Where does it go? Infinity. Yeah. Yeah. It goes way, way, way up here. Now, granted, if we were to take the angle's down to a negative 90, then our limit is negative infinity, okay? And you guys may know that this pattern will repeat. So because it says a domain error, because it says undefined, just because, so we have to look at our limits. So based on our function, it approaches one number from one direction, but it approaches a different number if you come from a different direction. That's why it's actually undefined. But if we apply it to real life here, and knowing that we're only using angles from 0 to 90, then at 90 degrees, the tangent of 90 is infinity, specifically positive infinity in here. So I would have to be going infinitely fast. Is that possible?
Yes.
Not that I know of. So, but remember, this was ignoring friction. And in real life, we can have friction. We do have friction. So let's take a closer look. So this is going to be the wall of death example. Okay, wall of death. Dun dun dun. So we've got a vertical wall. So you might have seen this sometime in like maybe like a circus or something like that, where you've got bicyclists or motorcycles in this like small cage, and they'll go loop to loop, and they'll go around the sides, and they're not going infinitely fast. So something has to happen here. So here's our room. Here's going to be the center of our circular room here, and we are going to drive on the walls. Here we go, driving on the walls. It's also like because it's fair time. There's usually at least one ride in the fair where it's a big circular room, either outside or inside, and it spins you so fast that the floor goes out from under you, and you're stuck on the wall, or maybe you're on like these things that kind of slide up as it goes. Yeah, like the Gravitron or something like that.
It looks like a UFO.
Yeah.
We went on it yesterday.
Very nice, very nice. I am not. I love fair food. I don't really eat a whole lot of it now at this point, but the rides, I'm really not much of a spinny ride person.
Chicken deer made me get
No.
I went on the one roller coaster that was on the street. So
Yeah, nice,
no,
nice.
it was not.
Okay, so I have my picture. FBD comes next. We've got our force of gravity points where? Down. Yeah, it always points down, guys. What else? What other forces are acting here?
Normal forces.
The normal force is pointing which way? That way? That's weird. Well, the surface is right here, so he's right. And friction is definitely required here. Where will friction point? So remember, this is sliding friction, and it's always going to point parallel to the surfaces. So in this case, our surface is like this, so it's either got to point up or point down. Which one is it? It has to point up, because where does the car want to slide? It wants to slide down, so the friction force has to point up. Okay? And we are going to assume that it maintains a constant height, so the y direction forces are balanced. Okay? This is just like if I were to hold a book against the wall. So I'm not spinning to make it stick, but I have to exert an Fn force to make it stick. Without the Fn force, it doesn't. And the friction is not there to keep it there. But as it slides down, or as it wants to slide down, the friction force has to point up. Okay, so which force serves the role as a centripetal force here?
Normal force.
A normal force, yeah, because it's pointing towards the center of the circle. So we've identified it, let's write it down. We've got our centripetal force is equal to our normal force, in this case, the wall of death. Huh? Okay. So then we're going to break it down. Our centripetal force is mv squared over r. She's actually Bye. Okay, so we got our mv squared over r here, and then the Fn, well, what is the Fn equal to? There's no force that it's going to balance out here, but we do know that our frictional force has Fn in it. So let's start there. Okay, so if our friction is equal to mu times the normal force, and we're solving for that because I need to substitute in here, so my Fn is equal to force of friction divided by mu. Okay, and then isn't the force of friction balanced by the force of gravity? Yeah, so my force of friction is equal to gravity, and gravity is equal to mass times acceleration due to gravity, mg. So we've got this mg over mu, that's going to be our normal force, so we're going to substitute into here. So mg over mu, and we're solving for v again. Look at that, the mass still cancels, it just doesn't want to stay. And algebra stuff, so we got v is equal to the square root of rg divided by mu. Now this is interesting, this is going to be the minimum speed now, okay? So the small speed that I can drive in order to not slide down the wall because I've maxed out my static friction force. This is how fast that I need to go. If I go slower, I slide down, okay? So notice again that the larger the cage is, or the larger my room is, the faster I have to be going. So typically when you see this in real life, like with the circus and things like that, the cage is pretty small, okay? So if the R is small, they don't have to be going as fast to drive on the walls. Here you go. But notice that there's an inverse relationship with our mu. The more friction we have, the slower I could go and still maintain the circular on the wall action. But the less friction I have, the faster I have to be going to maintain that circular action on the wall. All right, so we see in all three of these cases, we see that we're doing the same thing. We are drawing a picture. Then we're going to draw our FBD. Using our FBD, identifying where the center of our curve is and which force, or maybe part of a force, serves the role as the centripetal force. Once we know which ones are equal, we're going to set them equal to each other. We are going to expand it. Keep in mind that typically some of our things are going to be at rest, or in one direction, there's usually at rest action, so I can set those forces equal to each other. That's going to help me break down those equations and solve for whatever we need to. All right, let's take 5, and then once we come back, we will hit up the conical pendulum and wrap it up with roller coasters. All right, let's take 5. Will be one where there's not one right there, but if you see the planets hanging from the strings here, so we will replace them with pigs that have wings. So pigs are going to fly in physics class here in about a week. So the idea here is the pig is going to fly in a circle, kind of like that. So it's going to travel in a horizontal circle, but linked by the string, and it's going to fly at a constant speed. So if you look at the space that it takes up, or as it sweeps around the air, it's going to sweep out a shape of a cone. So that's why we call it a conical pendulum. A pendulum is kind of like a string that goes back and forth, which we'll talk in great detail about that in the spring. In the spring? Maybe right after Christmas. I don't know, I'd have to check my stuff, but absolutely this year, because it's on the AP1 exam. But the idea here is that the spring gives you your tension, and we're going to see how the speed is related to all of the other things. So here we've got our ceiling and then our mass attached to a string. Let's measure our string length L, and then we could also measure the angle from the vertical direction. That's going to be our angle theta. And so this is a conical pendulum. So we are going to take a look at it again, like we did our car examples, side view as it goes away from us in a circular path, kind of like that, where that's going to be our center of the circle. So let's take a look at our forces here. We, of course, again, have the force of gravity, which points down, and the tension, which points wherever the string does. And those are the only two forces that we have, tension and the weight. So what serves the role as centripetal force here? Tension, all of tension? No, only a part of this tension. So let's break up our tension into its two components. Hey, this sounds familiar, doesn't it? Yes, it's like our banked car example. So that's going to be our Ty, that's going to be our Tx. So which component, Ty or Tx, serves the role as centripetal force here?
TX.
Tx, there we go. So I've identified it, now I gotta write it down. So my Fc is equal to Tx in this case. That's our first step, okay? By the way, if ever we're doing an FRQ and we're asked to derive an equation, but you really have no idea what to do, write down something. Write down some equation that you think might be useful, even if you don't know how to get to where you need to be. That might get you 1 point, okay? And that 1 point might make the difference between a 2 and a 3, or a 3 and a 4, or a 4 and a 5, okay? Well, yeah, but the difference between a 1 and a 2 really isn't that all special, because both of them need to fail. So.
Wow.
How or wow?
I said wow.
Yeah, wow. Yeah. You know, what's also wow is how many 1s and 2s we typically have.
Well, yeah, because like everybody doesn't always do that good on it.
Correct. Yeah. The AP Physics 1 is notoriously difficult. It's
No,
got
my-
it's got either the lowest pass rate nationwide or one of the lowest pass rates
It has a
nationwide.
All of my cousins that are engineers and they're taking like physics 4, all of them failed this physics test.
Yeah, it's hard, y'all.
Yeah.
It's hard. But just because you don't do well on the AP exam has no bearing whatsoever to how you'll do on the IB exam if you continue on that path.
Okay, glad you said that.
Most of my students pass the IB exam even if they pass or failed the AP exam. It has no bearing whatsoever. And yeah. Let's get back to our equation here. So we are going to break it down again, mv squared, oh my goodness, over r. On that side, my Tx. So this is going to be exactly like our banked car problem, where the angle between our tension and our Ty is going to be that same angle theta, because this is alternate interior angles. And we even use our tangent function to connect our Tx and our Ty. So our tangent of theta is equal to opposite over adjacent. Again, that's going to be Tx over Ty. And keep in mind, again, in the y direction, it's at rest. So I can say my y direction forces are balanced. So my Ty is really equal to Fg, and Fg equals mg. So I can rearrange this equation, solve for Tx. So Tx is equal to Ty times the tangent of the angle, and I'm going to substitute mg in for Ty, so we get mg tangent theta for our Tx. I'm going to substitute into my master expression here, and we can go from there. So I'm going to solve for v here. Once again, the mass cancels out, like it likes to just run away from us, and we get the square root of rg tangent of the angle. And that would be great, except the problem tells us that we can only use m, l, and theta. I have r in there. I need to substitute something for r, because r can't stay. Okay, well, let's draw it. R is just the radius of the circular path. And r and the length of our triangle and the height here, that forms another right triangle, does it not?
Yeah.
Absolutely. So if I used a trig function that contains L, which is the hypotenuse, and R, which is the opposite,
Say it again.
which trig function contains both the hypotenuse and opposite?
Cosine.
Sine, there you go. So sine of the angle is equal to opposite over hypotenuse. Opposite is R over my hypotenuse L. So then I get an expression R is equal to sine theta times L. Okay. Just a second. My wife needs to go to the doctor and my son has work to do, so I got, I did post on rooms that help session is short today. I can still help you for a short amount, but I need to get home sooner than later. Okay. All right. So let's plug in R here. So there we go. So V is equal to the square root of L times G times sine theta tangent theta as well. And technically we could try to move around like the sine and tangent and stuff and combine using some trig identities, but we're just going to leave it as is. That is as nice as it's going to get. So here we have our speed of our mass on a string as it goes around in a circular path. So keeping the angle the same, but lengthening my string, I would have to go faster. It would have to go faster with a longer string. And then notice for both the sine and the tangent, the bigger the angle, the larger the sine and the larger of the tangent are. So the faster it is, the larger the angle, kind of like as I swing around my lanyard here at a very slow speed. And then as I speed it up, the angle with respect to the vertical has increased. So with more speed, we get more angle, kind of like that. And like our car example, it will be impossible to go fast enough that it would be completely completely straight across, because we still have our weight vector, that there has to be a little bit of the ty to balance out the weight. So it can never be truly a horizontal string here. There's always a bit of an angle. All right, our conical pendulum is done. Last but not least, our roller coaster examples. If you go with us to Busch Gardens, you will definitely take advantage of this topic. You will have a lab to do, and one of those labs deals with one of the rides, and you guys get to choose, and there's a good chance we will have something about circular motion in there, and this problem is it. So here we go. All right, so I'm going to erase this. Last chance to take a picture. You need to. Here we go. All right, here we go. Here we go. All right, so there are 3 parts of the roller coaster that we're going to talk about here. All right, 3 parts. So here it is. So 1, 2, and 3. So we've got the hill. So imagine we've got a cart and it goes above on top of that hill here. Okay, so we've got our hill. That's going to be our first one. Second thing that we'll look at is upside down in the loop-de-loop. Okay, so we've got our upside down. And then last but not least, we've got at the bottom of the loop. Bottom of the loop. So 3 situations here using a roller coaster example. All right, so let's take a look at our hill first. So the circle part of our track may kind of look like that, where the center is below the cart. Okay, what forces are acting on the cart?
NG.
The force of gravity, yeah, that points down. What else?
Fn.
The normal force, where does that point? It points up because the track is underneath the cart is on top of the track, the cart pushes down on the track, so the track pushes back up on the cart, Newton's third law. But the real question is, are our forces equal?
I
No.
say no.
No.
Yes.
Why not?
Wait.
Why do you say no and why do you say yes?
I don't know.
No?
When I think of like a roller coaster, when I think like I'm at the top of a hill, I feel like the speed I got up like pushes me up instead of down. So I'm not pushing on the ground as hard as I would have if I'm like standing still.
Okay. All right. Jordan, you said yes, that they would be equal. Why?
I don't know.
Okay.
I think I know that.
All right. So if we're going in a circle, there has to be centripetal acceleration, right? And that has to point where? Towards the center. In this case, the center is where? Down. So here's our object, our center is down. So in the radial direction, all right? So in this case, not only do we have one force, but we actually have two forces acting in that direction. One force is pointing towards it and the other force is pointing away from it. We've got to add together our forces here to get our centripetal force. But since there is a centripetal force, I have to have an unbalanced force. They cannot be equal to each other. One has to be less, one has to be bigger. So, if the center is below, which force has to be bigger here? Fg. There we go. Remember in the elevator example, how our weight didn't change, but the Fn did based on the motion of the elevator, and our scale matched what our scale matched what the Fn was, and that related to our apparent weight. How did we feel? Did we feel lighter or did we feel heavier? So same thing happens here. So our Fn is less than our Fg, so Fg is more. So I've identified, hey, I've got to add together my Fnet serves the role as centripetal force here. All right, so here we go. Let's take a look at our hill. So my Fnet is equal to Fc. Now they are pointing in different directions, so we have to establish which way is positive. I always choose the direction of the acceleration to be positive. That's my rule. I like to keep things nice and neat. So that means for the hill, down is positive and up is negative. So the Fg is positive, my Fn is negative. So when I break down my Fnet here, I'm going to write it like Fg minus Fn, because I'm adding together my two forces. And they both can be positive because they're pointing in opposite directions. All right, so we're going to break this down, mv squared over r, just like we had for the last three problems. And so I'm going to solve for v again, because I want to know how fast the cart is going as it goes over that hill. Okay. In this case, the mass doesn't count or cancel, at least not yet. But I will break down my Fg into mg. So mg minus Fn, and I'm going to multiply by r, and I'm going to divide both sides by the mass and take a nice square root. So here we have the speed of the cart as it goes over the hill. Now, I want to say, let's see, so let's not take a modern coaster, let's take like a very unsafe coaster, like a mining cart. Like if you've ever seen Journey to the Center of the Earth, or Indiana Jones. I think the Temple of Doom has a cart thing associated with it. And sometimes the track gives out, and so the cart gets airborne. So this is kind of like that idea. I want to know how fast can it be going and still maintain touching the track. I don't want to go flying. I want to go just fast enough that my butt lifts off the ground, and then I stay on the track here. Okay, so I'm trying to find what What is my V maximum? Okay, so I'm going to change this general equation, and I'm going to specify it, and I'm going to use blue now. Okay, so maximum is going to be the blue parts. So if this is going to be as fast as possible, this number in here must be as big as possible. And we learned from the elevator problem that I can't change my weight, but the Fn can change. So if this difference has to be as big as possible, then Fn has to be as small as possible. What's the smallest possible?
0.
0, absolutely. So our V maximum occurs when our Fn is 0. Okay, so at that point, my masses actually get to cancel, and I get my Vmax is equal to the square root of Rg. Oh, look at that. Look at that, my marker's dead. Here we go.
Oh.
I am not impressed. Okay, so now again, notice that our mass canceled out, so it doesn't matter if the roller coaster car is full of people or not, which is why it's okay for them to test when it's empty, because it's not going to change things if it's empty or full. Very interesting. So, but we see here that the size of our hill, the larger the hill is, the faster I can go over it, and my butt just lifts off of the seat. But if it's a small type hill, I have to be going slower to maintain contact with the track. Okay, good, good, good. Let's take a look at our next one, upside down. Jordan.
Do you think it's possible for roller coasters to skip tracks?
To skip tracks?
Like,
To jump?
yeah.
I mean, yes, it's possible, but no, it's definitely not safe. Yeah, it's the only way that you would be able to switch tracks is if it happens in a controlled and slow fashion. Like, I remember, it's been a while, but in Animal Kingdom, the Expedition Everest ride, where you go up and you actually pause at the top, and if you look behind you, the track is actually moving, so it moves your car from the track that you came in at, and now it shifts, and now you're going backwards on a completely different track.
How they do that in Tigers, like there's a level and then the track drops down.
Yes. Yep. So, but yeah, so yes, it is possible, but only in a slow and controlled fashion. Good questions. All right, upside down. Let's take a look here. So we've got our picture. Let's take a look at our forces. We've got our force of gravity pointing down. And where does the normal force point?
Also down?
It points also down. Because remember, it has to point from the surface onto the object. If the object is below the surface, the Fn has to point down, because that's where the object is. Yeah, so my Fn and my Fg are both pointing down in the upside down portion. Very interesting. So I'm just going to say down is positive since both of them are pointing down. And again, my Fnet serves the role as my centripetal force. So in my upside down portion here, we've got our Fnet is equal to Fc, and we have our Fn plus our Fg this time is equal to mv squared over r. I'm going to do that same thing. I'm going to solve for v. Okay, solve for v. So I'm going to multiply by r and divide by m times this combination Fn plus Fg, or I'm going to break that down into mg now. Fn plus mg is equal to my speed, but I don't want just speed. I want to know how slow I can go and still make it around that top of the track and not fall off as I'm going down. Okay, it's kind of like if I were to release a marble on top of this contraption here, based on where I put it, it may or may not have enough energy to make it all the way around. You guys that used to play with Hot Wheels, you used to do this all the time, okay? So based on how fast it's going, it needs to be going a certain speed to make it all the way around without falling. So that's what we're doing here. Let's change the color. So now I'm going to look for the minimum speed, okay? Because I need to get at least this fast in order to stay on the track. So now I'm going to change it to the small speed possible. And for this particular expression, again, I can't mess with my weight, but my Fn is going to be 0 if this is going to be as small as possible. And my masses cancel, and I'm left with, so my Vmin is equal to the square root of Rg. Ah, well, it's the same equation for the maximum on the top of the hill and the minimum speed upside down inside the loop. How very interesting.
So the velocities are equal?
Say what?
So the velocities would be equal?
Well, the maximum velocity on the hill and the minimum velocity on the upside down would be equal. Yes. Now, usually in roller coasters, if it's like this, then you're not going to be going as slow as possible. That's more like, actually, Tigris goes up, does it? It has one loop and then a weird thing on the top. But I remember when they used to have like the pirate ship ride. You know, it could go back and forth, and it goes up more and more each time, and then it kind of, sits there like a couple seconds, and then it moves around. I was never a big fan of that. No. I like my loops to be fast. Okay.
Never mind. The Ring of Fire, you've heard of that before? Is it the Ring or the Wheel of Fire? You remember?
I'm not
It's a
sure.
ride that they're, I don't want to understand what exactly it is, but ride where they have a cage around you.
Yep.
When the thing is supposed to go around your loop.
Yep.
Last time I did that, I just hit my head on the cage.
Oh no.
This is why I don't choose Carl.
Yeah. The whole like, I mean, it's cool that it can break down and be put back together each time that they move to a different city. But then again,
Dangerous.
that's a lot of things to, yeah. So, but it is what it is. So, last but not least, let's take a look at the bottom of our loop. So this is where we typically pull the most G's. And when I say G's, I mean the acceleration that you are experiencing, or how much force you feel being pushed into your seat. That's going to be the number of times of the acceleration due to gravity. So like if it says that this ride pulls 3 G's on this particular curve, and when you look at your labs, some of them have graphs about where the G-forces are in the ride itself, which is really, really cool to look at. But the G-force is really just the acceleration that you're experiencing as a factor of G, or 9.8. So 3 G's means that you are experiencing an acceleration of 3 times 9.8. At Busch Gardens, there is a ride. I'm not sure about the Iron Gwazi because it's kind of new. I don't think they have a lab based on it yet. I gotta check for this year. But last time I checked, there was a ride that goes up to 5 G's at Busch Gardens. So yeah,
Is that secret?
I'm not sure. I'd have to look. So. All right, question? No. All right.
Are G's measured exponentially, like decibels?
No. It's G's are straight up that number times 9.8. Yeah. But good question. All right. Last thing here. So the bottom of the loop. So you will most likely experience the most amount of G's at the bottom of the loop, because that's when our Fn is going to be the biggest. We see that it's real small at the hill because our butt lifts off of our seat. right? We may or may not experience that with the upside down. In most cases, you'll actually be going faster than this, and so you'll still have some G's as you go upside down, but you will have the most amount of G's at the bottom of your loop, because let's take a look at our forces. Once again, my force of gravity points down, but my normal force points up, and my normal force has to be bigger now because the center is above it. So the centripetal force points up, my F net has to point up, and we are going to say up is positive in this case. So my Fn is positive and my Fg is negative for the bottom of the loop. So let's go to our equations. Once again, F net is equal to Fc. The combination of our forces serves the role as the centripetal force. So our F net is going to be Fn minus Fg is equal to mv squared over r. And in this case, we're not actually going to solve for the speed here. There's no real special case that we see here. It doesn't matter if it's going slow or fast, although if it is going faster, you are definitely pulling more G's. But let's actually solve for the G-force, or how much force we're feeling. What is the normal force that we are experiencing here? So we're going to solve for Fn. We're going to add together, or add over our weight. So we got our mv squared over r plus our mg. And this is really where we can stop. So we've got our weight term plus the additional term for how fast we're going. And the faster we're going, the more G-forces we are experiencing. Very cool. So we see in every one of these examples that we drew a picture first. Pictures help. We drew our FBD. Crucial, because we got to see what forces we have and where they're pointing, so that we can identify which force or forces or part of a force serves the role as centripetal force. Once we identify what it is, we are going to set them equal to each other. We're going to use our equations and work it all the way down to where we need to. Okay? All right. So we've got about 12 more minutes left in class. Feel free to start on your pods. The quiz is already up. And then next class, we are moving into orbits. Remember, I have given you a new format. You can either continue reading in the book, which does give you the most amount of info, but a good plan B, or if you're just a visual and auditory learner and you want to watch the videos, then that is an acceptable plan B as well, okay? But I would encourage you, if you are wanting to pass the AP exam and do as well as you can, I would definitely start with the book and maybe watch the lessons too. Okay, but if you only have to do one, do whichever one you're most comfortable with, because I know that we all learn in different ways. So if you're more like, I need to read the book, then go for that. If you're more like, it's much easier for me to watch something, and then you can still take notes on either one. So you've got choices available to you. All right, so there you go. You can use the rest of your class time to work on that, and I'll be here.